Okay, we're going to start talking about nuclear chemistry now. This we're not going to spend a lot of time on because the AP exam does not go over it in a lot of detail. So it's something that I actually enjoy talking about, but we're only going to spend 5 days on it. Your next test is actually this Friday, this upcoming Friday. But it is worth talking about a little bit because there are some questions on it, usually on the AP exam. And I think it's interesting stuff, so we'll just go ahead and talk about this. It's been a while since you talked about nuclear chemistry, I know. It's been since the beginning of last year, if you took chemistry here at Holt last year. So it's going to take a little bit of refreshing, but I think this will come back to you guys. We just got to remember a couple of things here. First of all, the mass number and what that means. That's just the addition of protons plus neutrons. So if we count up all the protons and neutrons in an element, that's the mass number. The atomic number tells us the number of protons. If it's neutral, it also tells us the number of electrons. Okay, and then just some terminology here. Nucleons, that's just a fancy term for all of the subatomic particles in the nucleus, which is basically the protons and the neutrons. Okay, so nucleons is, again, just a fancy way of saying subatomic particles in the nucleus. I think that's all I need to say about that. Number of protons is the atomic number. We already talked about that. Protons and neutrons together is basically the mass of the atom. The electron is so small, relatively small, that we don't really even worry about that. Okay, isotopes. Again, we talked about this in the last unit as well, so we don't need to talk about this much. But some elements, some atoms of the same element will have different numbers of neutrons, and that causes them to have different masses. Okay. Some of those isotopes are radioactive, which we're going to talk about in a minute. Uranium's an example here. Uranium-234, uranium-235, and uranium-238 are the three naturally occurring isotopes of radium. Uranium-238 is much more abundant than the other two types. The other two types are a little bit less stable, and so they radioactively decay a lot quicker. Okay, so again, nuclides, just a terminology thing there. I think we already talked about that. Nuclides, just a fancy word for nucleus. Okay, and some isotopes are radioactive, just depending on how many protons and neutrons they have, or the ratio of those protons and neutrons. We're going to call those radionuclides. If they're radioactive nucleuses or nuclei, then they're radionuclides. And there are several ways that these things can give off radiation. We talked about all of these last year, so again, I think it's going to come back to you. But the different types here, we've got an alpha particle, or alpha decay, and that happens when an element loses an alpha particle. Okay, so an alpha particle is basically just a nucleus of helium, which has 2 protons. You can tell that from the atomic number 2, and it has 2 neutrons. You can tell that from the mass number of 4 minus the atomic number of 2. So 2 protons, 2 neutrons in a helium nucleus, and that is what is sort of spit out from the atom when it undergoes alpha decay. So notice this uranium here starts out at 238, goes down to 234, and the other 4 are accounted for right over here in the helium nucleus. Okay, so it starts out with 238 protons and neutrons, ends up with 234 protons and neutrons, and the other 4 are with helium. And then the same thing down here with the atomic number. 92 protons to begin with. When it spits out that helium nucleus, now it goes down to 90 protons, and the other 2 are in the helium, or in the alpha particle that gets ejected. So these things, you can usually add up the mass numbers on one side of the equation, and they should be equal to the mass number on the other side of the equation. Okay, 234 plus 4 equals 238, and the same thing with the atomic numbers. You should be able to add them up on one side of the equation. They should equal the sum of the atomic numbers on the other side of the equation. Alright, sample problem here. What product is formed when radium-226 undergoes alpha decay? So we don't have to do this, but we might as well just write the equation for some practice here. Radium has a mass of 226, and if you look on your periodic table, its atomic number is 88. Okay. When that undergoes alpha decay, it's going to give off a 4,2 helium nucleus. Okay. And so then, because the mass number is decreasing by 4 here, this is going to end up being 222, and the atomic number is decreasing by 2, so this is going to end up being 86. Whatever this particle is, it's going to have a mass of 222 and an atomic number of 86. And that's where you have to be careful. You don't rewrite Ra over here, because once this has an atomic number of 86, it's no longer radium, it's now radon. Okay? Hopefully that makes sense. Beta decay is another type of radioactive decay that can happen. And basically what's happening here is the nucleus spits out a high energy electron because of the change of a neutron into a proton. Okay, and so the effect that has when a neutron, which is you're going to write that, it'd be 1, 0, N, gets changed into a 1, 1, P, then you might notice there the atomic number goes up by 1. Okay, so we're changing from 53, atomic number 53, to 54 because now we've made another proton in the nucleus. Now we have one less proton than we had, or sorry, one less neutron than we had, but the mass number is just the sum of the protons plus the neutrons. So if a neutron gets changed into a proton, that's not going to change the mass number because they're still the same total number. Okay? And so that's why the atomic number here goes up from 53 to 54 with beta decay. Positron emission is another way that something can radioactively decay. And a positron is sort of like the opposite of an electron. It's got the charge, the positive charge like a proton, but it has the mass essentially of an electron. So when this happens, when you have positron decay or positron emission, it's actually the opposite process happens. You have a proton being changed into a neutron, okay, which causes the mass, the atomic number, sorry, to go down by 1. So this carbon here changes into boron, goes from a 6 to a 5. And then the nucleus spits out a positron, okay, as that transformation occurs. Gamma emission, we just need to talk about that. Gamma emission actually happens, it's kind of an awkward place to put this in a set of slides, but gamma emission happens with pretty much all of these other processes. With alpha decay, gamma radiation is given off. With beta decay, gamma radiation is given off. With positron emission, gamma radiation is given off. And so this is just the high energy that is given off when these particles undergo this nuclear reaction. And we're going to find out later why so much energy is given off. Actually, some of the mass of the nucleus is being converted into energy when these things decay. But notice there's a 0, 0 here next to the gamma symbol. That's just to show there are no protons, there are no neutrons that make up the gamma rays. It's just energy. Electron capture, or K capture, that's sort of the opposite of beta decay, because instead of an electron being ejected from the nucleus, actually one of the electrons outside the nucleus is captured and brought into the nucleus. And the result there is again a change from a proton into a neutron. Okay, so again, you're going to see the mass number stay the same, but you're going to see the atomic number go down on this kind of process. Okay? Alright, so let's do a couple sample problems here. Nuclear equations for the following processes. Mercury 201 undergoes electron capture. Alright, so mercury is Hg, 201 is the mass number, and the atomic number for mercury is 80. And it's going to undergo electron capture. So because it is capturing an electron from outside, we're going to put the electron on this side of the equation. So negative 1e, okay? And again, because in this process a proton changes into a neutron, then whatever we end up with over here, it's going to still have a mass number of 201, but now it's going to have an atomic number of 79. And the element with atomic number 79 is gold. So that's kind of interesting, because alchemists were constantly trying to figure out if they could make gold, and turns out it can be made from mercury if you have radioactive mercury that undergoes electron capture. But we can't really make that happen, it just sort of has to happen naturally, so unfortunately for the alchemists. So that's how you would write the equation for that one. Now notice everything's balanced here. If you add up the mass numbers on the left side of the equation and the mass numbers on the right side, it's 201 on both sides. And then 80 minus 1 for this electron here. That gives us a total of 79 on the left side and then 79 on the right side. Okay, next one, thorium-231 decays to form proactinium-231. So thorium is TH. Let's see if we can find it on here. Atomic number of 90, mass number 231, and that's going to decay to form proactinium. So let's leave ourselves some room here, because this one's not actually telling us how the decay is happening. We got to figure that out. So proactinium. Proactinium is actually 91. Atomic number 91. And its mass number is still 231. Okay. So whatever process is happening here, we're not changing the mass number. So this has got to be one of the conversions from a neutron to a proton or proton to a neutron. So it looks like here, because this is going from 90 up to a 91, that we're converting a neutron into a proton. And the kind of nuclear decay or radioactive decay that does that is when we have beta decay. Okay, so this is a beta decay reaction here. An electron is being given off, and you figure that out just by looking at the atomic numbers here and seeing which ones need to be well, whether it's increasing or decreasing from one side to the other. Okay. All right, let's talk a little bit about neutron-proton ratios here real quick. So there are repulsions between the protons and the nucleus, and we know that because protons are all positively charged, and positively charged things tend to repel one another. Okay, so the question then might be, why doesn't the nucleus just fly apart because these protons are pushing against each other? Well, it turns out there's a strong nuclear force that helps keep that from happening, okay? And strong nuclear force is complicated. I don't completely understand it. But neutrons sort of play a key role in that, in keeping the nucleus intact, okay? Now, there needs to be a certain ratio of protons to neutrons in order to have a stable nucleus. That's what I just said. So, when you've got a smaller nucleus, something less than 20, and Z just means atomic number. I don't know why someone decided that Z would be atomic number, but it is. So for anything less than 20, if you look at this belt of stability graph over here, it looks like it's pretty close to a 1-to-1 ratio, okay? Neutron to proton ratio is pretty close to 1-to-1. As you get bigger, you need more neutrons to stabilize the nucleus. So you're going to have a bigger ratio there. So you might notice as you get to the bigger elements on the periodic table, their masses get quite a bit bigger compared to their atomic numbers. And so the reason for that is there's more neutrons packed in there because it takes more neutrons to help stabilize the bigger nuclei. Okay? And again, the shaded region right here on the graph shows the belt of stability. Okay? So if we continued going in a 1-to-1 proton ratio, you can see that would get outside of the belt of stability fairly quickly. And that's why you have to have more neutrons in there. If you're above the belt, there's too many neutrons, okay? And if you think about that, there's a couple of ways to get rid of neutrons by converting them into protons. So beta decay is one of those types that changes neutrons into protons, and so that helps the nucleus be a little more stable, so it would tend to decay that way. These things are always trying to get stable, these nuclei. Now below the belt, you're going to have too many protons, okay? So not enough neutrons. And so those would tend to decay by positron emission or electron capture, because both of those actually convert protons into neutrons, okay? And so that would help to stabilize that nucleus. Hopefully that makes sense. Now another thing that makes a nucleus unstable is if it's too big. So if you look on the periodic table, anything with a greater atomic number than 83, that just starts to get too big. So at that point, they're going to start to decay. And a lot of these tend to decay by alpha emission because, remember, the nucleus doesn't get any smaller with the other types of radiation we've talked about. Alpha decay is the only one that actually makes the nucleus smaller, because the other types involve a proton being converted to a neutron or a neutron being converted to a proton. Okay, so alpha emission is usually going to happen with things that are too big and they're trying to get smaller so they can get stable. All right, so mode of decay of carbon-14. So let's take a look at that. Carbon-14, there are 6 protons and 14 total nucleons there, which means that we've got 8 neutrons. Now, this has a Z, or an atomic number of less than 20. Okay, so we would expect this to want to be in kind of a 1-to-1 ratio. So basically we've got too many neutrons here. Okay, and the type of decay that changes neutrons into protons is beta decay. Alright, so we would expect probably this would be beta decay here for part A. And then for part B, we've got xenon 118. Okay, xenon has an atomic number of 54. 118. Oh, see, this is bad. Bad math. So that means that we've got 54 protons, 64 neutrons. Okay, and if we go back over here, sort of look at our graph. So 54 protons, we go up here, 64, kind of trace that up, 64 neutrons. That looks like it's pretty close to the belt of stability, but it might be just a little bit low, where maybe we have just a little bit too many protons. So what we might expect on that one then is that it would undergo either positron emission or electron capture, one of those two. Okay, so positron emission. Now that one's actually pretty close. So but it looked like it was on the low side as far as having more protons than neutrons. Okay, so radioactive series. When something decays, it doesn't just decay once. It's not just going to spit out, you know, a bunch of alpha particles and then be fine. This is going to happen in a long series of events, and some of these decays take a lot longer than others. And so, for example, with uranium here, if you're looking at uranium, it decays into thorium, then decays into proactinium, then decays back into uranium, then decays into thorium, then decays into radium, radon, polonium, and so on. Okay, and eventually, a lot of times, these series of radioactive decays will often end with lead. because lead is one of the most stable, bigger elements. And so these nuclei are trying to get stable, and a lot of times they end up going to lead. Okay? Now just some trends here as far as stability is concerned, and I'm not exactly sure why this is the case. It really just has to do with the ratio of the protons to the neutrons in there. But if you've got nuclei that have 2, 8, 20, 28, 50, or 82 protons, or 2, 8, 20, 28, 50, 82, or 126 neutrons, those are going to tend to be more stable, okay, for whatever reason. And you really don't have to worry about that. You're never going to be asked a question like that on the AP exam, okay? Just kind of for your own information, there are certain kind of magic numbers with the nuclei that seem to make them a lot more stable. And then even versus odd seems to be an issue as well. If there's an even number of protons and neutrons, then it seems like those are more stable than the ones that have odd numbers. And again, for whatever reason, that seems to be the case. Okay? So, based on those trends that we just talked about, let's do a sample problem here. Which of the following are especially stable? Okay, so let's go back for a second. Look at our rules here. Nuclei with 2, 8, 20, 28, 50, or 82 protons, or the same for neutrons, tend to be more stable. Okay, and then also if they have an even number of protons and neutrons. So helium here seems to fit that description on both counts, okay, because it has 2 protons, atomic number of 2, and it has an even number of protons and neutrons. So this one we would probably call especially stable. Uh, 40-20 calcium. Okay, so again, 20 I think is one of the magic numbers here. Let me make sure. Yep. So 20 is again one of the magic numbers, and it has an even number of protons and neutrons. So this one would also be especially stable. Then if you look at TC, I don't remember what TC is. I should probably know that. Technetium, maybe? Anyway, regardless of what it is, it definitely does not fall into that that magic number of protons, and it has 55 neutrons, so it doesn't fall into the magic number for neutrons either. It does have an even number of protons and neutrons, but that's going to contribute to stability, but it's not going to be really that stable compared to the other two. Okay, so the ones that are especially stable would be the helium and the calcium. And that's stable in the nucleus. Okay, calcium is fairly reactive because it wants to get rid of 2 valence electrons, but that's just regular reactions. We're talking about radioactivity here. Okay, nuclear transformations. You can encourage those to happen by slamming particles together very, 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 very hard. Okay, and you do this basically just by giving it bursts of magnetism as a charged particle goes by, and eventually, after you build up enough speed, you've given it enough bursts that speed it up every time it goes by, that you just crash these things into one another, and you see what happens. Okay, these things have to be really, really big. Okay, because we have to really get up the speed of these things before we crash them into one another. Alright, I'm not real worried that you know how to do this. In fact, we might just go ahead and skip this one because the video is getting a little bit long here. Yeah, I don't think you're ever going to see this on the AP exam, so we'll just skip over this for now and finish the video. Next time we'll talk about how to figure out radioactive decay and how long it takes and that sort of thing. So we'll just go on to that from here, okay? Make sure that that's the end of what I want to talk about. Yeah. So we'll get to the next part next time. All right, so that's the first part of nuclear chemistry. Hopefully that makes sense. See you next time.